Moreover, if we saw this as this is the positive direction, as it's getting slower on the way up, it reaches this 0 point and then it speeds up on the way down. The speeding up part, the acceleration is positive, which is what the graph shows. So this looks like C is our answer, but we're not going to quit. We have something falling, then bouncing elastically off a hard floor. So this is something, if we drop it, its V0 is going to be 0, and then the velocity is going to increase. And again, that's the opposite of what we see. We start out with a fast velocity that goes to 0. This is the opposite. So that's why we're at choice C. So we have a person driving along with a car. We have our positive direction, our negative direction. It's moving along. We have a V0 that's unknown, and it slows down and it comes to a stop, and the final velocity is 0, and this distance is 20 meters. The acceleration is constant, and this happens in 4 seconds. Can the speed of the car immediately before the brakes were applied be determined? Well, what is undervalued in physics is the power of average velocity. If we have the average velocity as delta x over delta t, well, let's see. We know this was 20 meters in 4 seconds. So that means the average velocity was 5 meters per second. Well, that's the average velocity. The speed of the car immediately before is v0. Well, average velocity is also v plus v0 over 2. We know the final velocity is 0. So that means the average velocity is v0 over 2. The velocity at the end is 0 because it comes to a stop. So now if we rearrange that equation, we have twice the average velocity as the initial. So twice times 5 is v0. So the initial velocity was 10 meters per second. Can the speed immediately before? Well, the answer is yes, and we can tell you it's 10. So the nose, and let's just see, because the acceleration is needed. No, we don't need the acceleration. We don't even need to use that equation. Fundamental relationship defines velocity contains acceleration. Well, that's false. Yes, by dividing the distance 20 by 4, that's false, because that will give us the average velocity, not the initial velocity. Yes, by determining the average speed while braking and doubling it, and that's exactly what we did. Choice B. Next, we have a block released from a rest. So we have a V0 equal to 0. It has 3 rough sections. So this is rough, and this is rough, and this is rough. So let's think through what that's going to mean. That means there's going to be an acceleration here. And it's going to continue to travel through the rough patch, but the acceleration will be less. And then this acceleration will return to the same as acceleration as this. And then here the acceleration will be less again because of the friction. And then this acceleration will occur again. And then this will be less acceleration. And then we'll have that normal acceleration again. Which of the following will allow for the best estimate of the block's instantaneous acceleration when the block is at the midpoint of the ramp? The instantaneous acceleration is going to be the acceleration that it's going to experience over that interval. Now, we're not told that these 3 rough sections are rough in exactly the same way. It's not like we're being told there's a piece of sandpaper here and it's identical to the sandpaper here and here. All we know is that they're rough, but we don't know that they have the same roughness. But we do know when it's not rough, the acceleration should be the same because that's determined by the angle. So, how will we find the total distance traveled by the block and the total elapsed time? Well, the total distance and the total elapsed time is going to be this. It's going to include all these other things. That can't be right. The final speed of the block and the elapsed time. Again, even if we know the final speed here and the elapsed time, there's just too many unknowns or chunks in there. So the distance between the points just before and just after the midpoint, and the time it takes the block to travel between them. So if we have this point and this point, we can know that displacement, delta x, and we can know delta t. That can give us the average velocity only. So it can't be c because that's only going to give us the average velocity. So we're down to d, and there's no choice e, so it must be choice d. But let's see if we can figure out why, or if we made a mistake and it's really a, b, or c. The speed at the block just in before and afterward. So if we know this v, and we know this v, and the time it takes, that would be the t. Acceleration is delta v over delta t. So yes, it's choice D. We need to know two velocities in the time interval between which those two velocities changed. 9, we have a velocity time graph. So we've got, we'll do our full Oizerga. Our origin is right here. That's important for us to know. We have positive values and we have negative values down here. So we found our origin. The y-axis is velocity in normal units, x-axis time. So therefore, any questions about velocity or time we'll read. The gradient is dividing those. So delta v over delta t is the acceleration. And the area, v delta t, is meters per second times seconds, or meters, which is the displacement. Great. So we've got a motion sensor creating this velocity as it moves toward and away from the sensor. Positive is the direction away from the sensor. So this is away, and this is toward. Which of the following describes the final position in relation to the starting position? So we want to know the final position in starting to the relation. Oh, so starting, the final related to the starting. Well, that's clearly displacement. Delta x equals x minus x0. And we're looking for the final position, which is x. So x is going to be delta x plus xo. All right, so if we want to know delta x, we've got to find the area. So we have this area here, which is positive, and we have this area here, which is negative. Now we can clearly see that the negative area is less than the positive area. So overall, in fact, probably if we take this block, it looks like it's approximately about equal to that. So you can see there's clearly a lot more red area. There's a lot more positive area. So XF is farther to the right, to the positive. And it's farther away from the sensor. Away from the sensor is positive. XF is farther away. True. It is not closer. Then XO and AX is positive. The average horizontal acceleration between 0 and 3. If an object starts at one location and it ends up at this is time 0, and at the final time they end up in the positive direction, then the acceleration overall must be positive because they went from here to here. Choice A. Question 10. At time 0 is moving to the right with the velocity v and can be modeled by this equation. So we have a v, let's put it in a way it makes sense to look at. So the velocity is minus 1.4 t plus 4.2. We don't need to see the units because we know what the units are in this equation. Minus 1.4 t plus 4.2. At what time does the object change its direction of motion? Now, its current velocity is positive 4.2. So we want to know at what point is the velocity going to switch from being positive to negative. And that switch occurs when the velocity is 0. So 0 equals minus 1.4t plus 4.2. 1.4t equals 4.2, and t equals 3.0 seconds. And that's that question.